Hypothalamus Artificial Intelligence, HI. Digital transformation powered by real-time autonomous and intelligent algorithms. Presents the short conference. Parallel and distributed analytics applied to transport and logistics chains. Conference prepared and edited by Jesus Velasquez Bermudez. His resume may be found on LinkedIn. The new way of mathematics is directly related to the parallel thinking, and today it can be said that like paper-based math, sequential mathematics for single-processor computers will be in the short term a dead language. As in the human brain, in the future only parallel mathematical thinking will be practical. The new analytics is autonomous, parallel, and distributed. The interested people must review the short conference. Sparse analytics and artificial brains. Autonomous real-time routing and distributed optimization. Industry 4.0 real-time routing. Challenge: modify the traditional vehicle routing process to access to the Industry 4.0 environment. Solution: it implies that all agents, the dispatcher and the vehicles, need to know what information they need to take from smart metering systems, and what information they need to provide to other agents to they make their decisions, to keep the system end-to-end on the path to optimality. This is possible using asynchronous parallel optimization methodologies. In the case of freight transport, the traditional process of planning logistics operations in a city could be carried out as follows. At the end of a period, for example, a day, or a shift, a dispatcher plans all routes to fulfill the deliveries, or pickups of the next period. This may involve solving the problem of routing vehicles with time windows on customers, optimizing an objective function according to the company's business rules. Even for small fleets of vehicles, this is a complex mathematical problem, when we consider all the limitations in real systems. The dispatcher generates the route, the sequence of clients, and possibly the route, the sequence of streets, for each vehicle that will be used that period. This schedule is fixed, and it may be considering static travel times for the entire period. That is not true. At the end of the period, the dispatcher updates the database considering the contingencies that occurred during the period, and will start the process again. Given the reality of the process, in which travel times are uncertain, and change dynamically during the period, the programming carried out cannot be optimal. To transit the path of optimality, a dynamic scheduling can use all the power offered by smart metering systems, like Waze, which, in any time, provides rich information for each truck. The best path, or a route close to the best, and a good forecast of the actual travel time. Additionally, it may be possible to obtain historical data on travel times, differentiated by time of day, day of the week of the month, etc. This allows the dispatcher to have up-to-date information to solve a vehicle route issue with time-dependent time and travel time windows, which should produce better results. The dispatch process can be adjusted as follows. At a certain point in the period, the dispatcher plans all routes solving the routing problem with time windows and time-dependent travel time, taking as input data the latest database updated by all smart metering systems, that is, the trucks, Waze, hydroclimatological, and traffic databases. This process would be carried out centrally, to generate a forecast of the route of each vehicle, to be used that day. Each route must be uploaded to MSD, a mobile smart device, such as a Raspberry computer, VDO, iPhone, or iPad, through which data is received from a SM, a smart metering system, such as Waze. During the route, at the end of service on a client, the MSD mobile device asks SM for information about the estimated travel times, and optimal routes to complete the route. With the new information, the MSD can solve a TSP, travel salesman problem, to recalculate the optimal missing route, that is customer service order, and attention times. MSD send that information to the dispatcher, so that, if necessary, it will rearrange the planning of all routes. The approach may be conceived as an artificial brain composed of a network of mathematical models, the VRP dispatcher, TSP problems in trucks, and the mathematical models provided by Waze, and the existing measurement systems. The communication between the algorithms of mathematical problems must be asynchronous, since events occur in the system. Two levels of interconnection can be visualized, with the dispatcher, to coordinate the entire system, and between trucks, to improve truck decisions. To establish the communication protocol between agents, the decoupled view of a routing problem can be considered, which may be solved using Bender's theory, Lagrangian relaxation, column generation, or cross-decomposition. These methodologies already include math communication between algorithms, to improve the solution of the integral optimization problem. Autonomous real-time energy optimization. Fuel consumption can account for up to 63.9% of the variable operating costs of a heavy ground transport fleet, therefore, it is a critical factor in the planning and scheduling of truck routes. In state-of-the-art cargo transport vehicles, the engines are electronic, digitally controlled, with telemetry capability of the nearby environment that optimizes fuel efficiency. This autonomous capability of modern vehicles can be called optimal short-range control. There is another level of operations planning of a fleet of vehicles that is long-range, and that must contemplate the full route of the vehicle, and the planned times of arrival. The importance of this planning is seen in the performance curve of an engine in which operating in a range of 1,100 to 2,000 revolutions per minute results in optimal performance between 1,500 and 1,800 RPM, according to the truck's provider. However, optimal power performance, with lower fuel consumption, is below 1,500 revolutions per minute. As in any vehicle, the compromise between speed and economy do not move in the same direction. The graph presents the differences in performance of the engines of 5 types of truck. So, optimizing energy consumption is complex because the consumption function is not linear and depends on factors that are the result of decision-making, such as vehicle charging and geoposition. Route-dependent factors, which can be divided into static, for example, slope, roughness, and dynamic, for example, traffic, route weather. While the mathematical problem is complex, the power of parallel computing, the effectiveness of optimization algorithms, and online databases, make it possible to solve it in the Industry 4.0 environment. This problem can be solved on MSD computers in vehicles. Finally, there are now in the world machines that think, that learn, and that create. Moreover, their ability to do these things is going to increase rapidly until, in the visible future, the range of problems they can handle will be coextensive with the range to which the human mind has been applied. In 1972. In the book Human Problem Solving, wrote by Alan Newell and Herbert Simon. Thank you very much for your attention.